Good day, everyone. We are Group 4E, consisting of Chuanyu, Hongbang Wu, and I am Po Yulin and Shenshan Li. Today, we are excited to present our final project on LLM-aided code generation for high-level synthesis. Our presentation will cover the following sections. First is the overview, and then the approach, and we will talk about the result we're doing for Lab 1, Lab 2, and Lab 4, and finally, our conclusion. Let's start with an overview. High-level synthesis tools have significantly advanced hardware design workflows by bridging the gap between high-level algorithms like C++ code description and hardware implementation like Verilog. Concurrently, large language models have revolutionized task automation, enabling the generation of high-quality, domain-specific code from natural language description. By integrating HLS and LLMs, we aim to streamline the translation of human-readable instruction into synthesizable HLS-compatible C++ code, thereby reducing development time and complexity. And one thing to mention is why we are transferring the natural language into the C++ code, not the Verilog. This is because the LLM is more capable to dealing with the C++ code, not the hardware description language like Verilog. So if we transfer the natural language into a C++ code first, and then use the HLS tool translate into the Verilog, the accuracy is actually higher than just using the LLM to transfer the natural language into the Verilog by 10%. So that's why we are doing this. So our project focuses on using the Verilog's LLM models to generate and optimize HLS code for three ECE6775 labs, Lab 1, Lab 2, and Lab 4. So in the first part of our approach, we started by generating appropriate prompts for the LLMs. We are using the ChatGPT-4 to generate the prompt. And these prompts were designed to instruct the models on how to generate LLS code for Lab 1 and Lab 2. We used various LLM models, including Cloud 3.5 Haiku, Llama 3.1, and of course the GPT-4 and Gemini, and also the DeepSeek. After generating the code, we compiled to check for the syntax errors. If there were any errors, we generated the code with adjustment to the prompt. This iterative process ensured that we could produce syntactically correct code. Next, we evaluate and compare the accuracy of the code produced by each model. This involved running the code and checking its output against expected results. We then synthesized the code to analyze resource usage, including VRAM, DSP, FLU table. This step was crucial to understand how efficiently the generated code was in terms of hardware resources. Finally, we applied the models to optimize the code. We synthesized the optimized code and compared to resource usage before and after the optimization to measure the improvements. So the Lab 1 focused on the coding algorithm, which is used for trigonometric calculation. We used various LLM models to generate the HLS code for this algorithm. The goal was to see how well each model could handle the task and produce accurate results. As we can see, the Gemini, most of the model can handle these tasks with only 1 to 2 trials. So this is a relatively easy lab for the LLM model. But for the Lab 2 was a bit more challenging as it involved the KNN algorithm, which is used for the classification task. This algorithm is more complex, so we had to run more trials to get accurate results. We used the same simple prompt for each model and adjust it based on the error encountered for both Lab 1 and Lab 2. So as you can see, the Lab 2, like for example, the Llama 3.70b have to try 4 times, but in the Lab 1, it only have to try 1 time. So the Lab 2 is more challenging for the LLM model. So as you can see, this table shows the overall error rate for sine and cosine functions generated by different models for the coding algorithms. As you can see, GPT-4o and Gemini Pro, and also the Cloud 3.5 Haiku had the lowest error rate, indicating their superior performance. Out of the surprise, the Llama is the performance is very low compared to the data size it had. And next, this table presents the design error rate and resource usage for the KNN code generation by different models. As you can see, the Gemini 1.0 Pro and the Gemini 1.5 Pro have the lowest error rate compared to others LLM models. So like DeepSeek, the error rate is impressively high. And GPT-4o, out of our surprise, it's also very high because GPT-4o is the mainstream LLM model we are using nowadays. And also the llama is also very high, vary from 85% to the 99%. It's like it's very surprising news for the llama failed on both Lab 1 and Lab 2.
And now I like to talk about optimization for Lab 1 and Lab 2. And after we completed the base code, we fed them to the same model and generate the optimized code. And we compare the latency and area usage of different codes. Here is a prompt for our optimization. In our program, if we generated code, we will compile it. And if it failed, it will fed the error to the prompt and regenerate. So the program could count the compilation attempts. This figure shows the compilation attempts for different modules, and we could see there are some failures. For this table shows using the llama module for codec design, and this is for base, and this is for optimization. We could see that the error rate is really high, latency is large, and there is no difference after optimization. But for Gemini 1.5 Flash and Pro, the error rates are all really low with small latency. And after optimization, we could see that it's reduced to less than 1/2. ChatGPT 4o has relatively small latency and small error rate, but DeepSeek doesn't work in these cases. This is the result for KN classifier algorithm for Lab 2. And for both llama modules, we could see the error rate is really high, latency is large. For Gemini 1 Pro, the accuracy for a k equals to 1 is low, but the latency just slightly reduced after optimization. For 1.5 Flash, the latency reduced, but the accuracy is too low. But for ChatGPT-4 and DeepSeek, we could see that the error rates are really low for these two, both about 10%. And the latency greatly reduced after optimization, which is about 217 times. So in conclusion, for Lab 1, Gemini works the best. For Lab 2, ChatGPT and DeepSeek are better. So we will use them in our Lab 4.
For the second part, we're targeting Lab 4 with LLM optimizations. We try to use LLM to replicate and improve the Lab 4 results through better prompt engineering. We experiment also with different models, compare performance and optimization strategies like the DeepSeek 01 and the Llama 3.2 70B. We try to minimize the latency while maintaining the resource constraint.
In Lab 4, we were tasked with improving the performance of binary neural networks using high-level synthesized optimization techniques, including unrolling, pipeline, array partition, array reshape, and array inline. The challenge was use LLM prompt engineering to apply these techniques skillfully to achieve significant latency reductions beyond the baseline performance. We follow 3 key steps. First, we finalize with HLS optimizations. We ensure the LLM understood the baseline code, the HL optimization techniques. The second step is to identify the bottlenecks. We target critical components like convolutional layer and density layer, which has the most potential space for improvements. 3. We use finalized prompt-based optimizations. Using GPT-4o, we finally refined the design through a multi-run prompt strategies. By systematically applying these strategies, we achieve outstanding outcomes. After 3 run prompts, the performance improvement achieved 150, earning full marks for lab 4. After 5 rounds pumped, the performance speed up achieved 1000. Exceeds all the results of other classmates. So, in conclusion, we introduced LLM-driven optimizations not only help us overcome these limitations, but also unlock new possibilities for performance enhancement.
In conclusion, our work highlights the transformative potential of LLMs in hardware optimization, particularly in HLS. By integrating LLM capability with traditional HLS tools, we effectively tackle challenging tasks and achieve groundbreaking optimizations, such as the 100 speed-up latency reduction in Lab 4. This project not only showcased a significant performance gain, but also deepened our understanding of HLS concepts, bridging theory and practice. As LLMs continue to revolutionize problem-solving and innovation, their strategy use can amplify human ingenuity and redefine approaches to complex technology challenges. We look forward to exploring further application in this domain. Thank you. And this is our reference knowledge.